Hey guys, welcome to Cougar Chem Tutoring. I'm Austin and I'll be running through part 1 of problem set 2 measurements here with you. Number 1, how many significant figures does the following figure have? Every number that's not 0 will always be significant, so I'll just put an X above all the ones that I know for sure are going to be significant. Now there are certain rules for zeros and whether they're significant or not. If they are preceding zeros, they're not going to be significant. Take the number 100, for example, and I could technically put zeros in front of that 100, but that doesn't change the value of this. It's not very significant in determining what that value is. So any preceding zero, including before a decimal here, is never going to be significant. Okay, so I'm just going to put an X through it, right, just like that, okay? Now, trapped zeros, trapped meaning trapped between two significant figures, are always significant. So that's going to be significant. By default, just by being between two significant figures, it becomes significant. Now, for this last zero here, it's trailing. It's a trailing zero, and there's a decimal here. A trailing zero after a decimal will always be significant. So this has 6 sig figs. Let me just emphasize this last one here really quick. Let's take the number 10. This last zero, this second zero here, is not significant until you put a decimal. Okay, this zero is now significant. Without the decimal, it was no longer significant. However, additionally, if I continue to add zeros, each zero after this will continue to be significant because this decimal is here. Okay, so the decimal is kind of the key factor here. If there's no decimal, if I just had the number 200, and the number 200 written as is only has one significant figure. If I put this decimal here, it now has 3. Okay, so that's how we kind of want to think about these. This ultimately has 6 just by those rules. All right, number 2, you're going to want to get your calculator out because for these problems, you'll want to do those like that because you'll have your calculator on the test with you. Okay, and so practicing with it now will help you a lot to kind of get the rhythm down for when you're taking an exam. All right, so significant figures in addition and subtraction. So it doesn't say here, but I didn't include it, but we should have included sig figs here as part of the instructions. So, and they want to give us to give our answers in scientific notation. So let's add these to get 2 together. When we do that, we get 1,080 grams. Now, for addition and subtraction rules, there are specific rules that we follow for significant figures. Notice how we counted sig figs here. That's not necessarily what we do for addition and subtraction. When we're adding 954 plus 126, okay, we have to be specific to the number that is least specific. Let me show you what I mean. Both numbers here are specific to the ones place. So my answer is limited to being specific to the ones place. So here, I'm going to include the 0, and especially when I write my scientific notation, I'm going to write it like this. Okay, I'm going to keep this 0 in here. Now it continues to be significant, and times 10 to the 3 grams, right? And that's how we like to do our significant figures because we've moved this decimal place over 3 times. Okay, and that becomes our answer. But we had to be specific to this place. If this had been, let's say, 950 plus 126, now I'm specific to this place because this 0 is no longer significant. Okay, and so my answer would have to be, let's see, if I did it this way, this would be 6, 7, 10. I would have to round this up to 1080. Okay, I would have to round it up to 1080, and then in my scientific notation, I would just put 1.08 times 10 to the 3. Okay, if that was if the answer was 950. Sounds a little bit counterintuitive, but that's kind of how we work with sig figs in Chem 105. For multiplication and division, we look at number of sig figs. So kind of what we did on the first problem, you'll want to do for each number that's involved in a multiplication and division. So here's 3 sig figs, here's 2. So my answer should come out in 2 sig figs. Okay, because I'm limited, my answer is limited to the least amount of sig figs. So I get, if I punch this in the calculator, I get something like 3.7931. But I'm limited to 2 sig figs, so I'm going to round this second number up to 3.8. So I'm going to get 3.8 milliliters. Now, this could be in scientific notation. The only problem is that we would have to put times 10 to the 0, and it's a little redundant to put times 10 to the 0. So we're actually not going to include it, and technically on a answer like that, you don't have to. All right, letter C here, we're doing addition and subtraction here, rules. So we got 0.00447, right? That's what 4.4 times 10 to the 7, 4.47 times 10 to the negative 4 is. And then I got this value here, 5722. Now I wrote it like this so you can kind of see I am specific to this place, right? This guy has all these values here, but those aren't significant. Those aren't going to play any part in my significant figures. So when I subtract this out, I'm going to get an answer that is specific to that one place, or I'm not going to get an answer that's specific to that one place, and I'm going to have to put my answer that is specific to that one place. So let me punch it in the calculator here, 5722. Okay, I get the following, 4.41278 times 10 to the negative 4. Okay, but notice that I had to be specific to this place. And so I'm going to put, that's this place right here. So I'm limiting my answer here to 4.41 times 10 to the negative 4. All right, last one. Now we're doing multiplication and division again. Honestly, just punch this straight into your calculator. But notice that we are limited to 3 sig figs, right? There's 4 here and there's 3 here. So my answer should be limited to 2 sig figs. And you end up getting 1.49931 times 10 to the 12th. Nanometers. Now, I'm limited to 3 sig figs, so I have to put my answer here into 1.49 times 10 to the 12th and kick off the 3-1 that was there, okay? So this would be my answer. All right? Hope that made sense. Hopefully, as we do some more examples here, it'll make more sense. All right, perform the following calculations for measured numbers. Convert your answers to the base unit for that quantity, and whatever that may be. Okay, so notice here that we're talking about the base unit. Base units are different from what you may hear as SI units. Sometimes they're the same, sometimes they're not. Just be wary of that difference. Okay, so the base unit just means if it's in milligrams, okay, the base unit would be grams. So we're gonna, whatever we get here, we're going to turn it back into grams. All right, so when I add this together, I actually get 108.76 milligrams. All right. Now, this is in, first of all, let's get our sig figs right? We're specific to this place here and specific to this place here. This is the least specific, so I'm limited to the 10th place here. So I'm going to turn this into 108.8. And we're in milligrams. And so to turn it into milligrams, remember 1,000 milligrams are in 1 gram. Okay, so that means in order to turn it into grams, I have to divide this by 1,000. Okay, to get it into grams. So that becomes 1.1088 and then grams. Okay. All right. B, 225.7 minus 88.23 micrometers. Okay, you can just straight up punch that into your calculator. And we get 137.47. Now, careful, I'm specific to this place here and specific to that place there. And so I'm limited to the least, the one closest to the decimal place. So I got to round this 4 up because I'm specific to this place. So I'm going to say 137.5. Now, this is in micrometers. And micro, if you don't know, is times 10. It's a millionth of a meter. Okay, so a micrometer would be a millionth of a meter, which is times 10 to the negative 6. So I'm going to say 137.5 times 10 to the negative 6th, which ends up just being, if I move this over 2 more places, 1.375 times 10 to the negative 4th. Okay, and this would be meters. All right. Okay, now we're doing with multiplication and division here. Let's just punch this right into our calculator. 2.76 to the 4th, 7.4 to the negative 2. We get, let's see, we get 2042 here, okay? 2042. Sorry, 20,424, okay? Now, this is weird because we got 3 sig figs here and 2 sig figs here. And somehow we got to get this number to look like 2 sig figs because technically I have to round down, right? I can't put this up into 5. I can't put this, round this to 5 right here because this 4 is too high. So I got to round this down. So that would be 20,000. But notice that there's only 1 sig fig here, right? We don't have a decimal to be able to determine where, or like that there are 2 sig figs here. So there are 2 ways to do this. Actually, I think one way to simplify this will be to turn this first into a meter. So when we divide by 1,000 millimeters to turn it into a meter, we get 20 millimeters, which actually helps us a lot. So or 20 meters, sorry. So we can either put 20 decimal and then meter, or we can also put 2.0 times 10 to the 1 meter, and either one of those answers would work on a test. Okay. All right, lastly, we are working with multiplication and division again, except we're also integrating another aspect that you haven't seen yet. We are using 2 different units. We're dividing 1 unit by a totally different unit, and you may not recognize this, but this is a mass over a volume, right? Mass and a volume, and that's actually a form of a density. So this is, we're calculating some form of density here, just to kind of show you what's going on. Okay, so we got 2 sig figs here and 3 sig figs here. Now, if I punch this in my calculator, 83 divided by 1.44 to the negative 3, okay, I get this large value, 57,638.888. Okay, now I'm specific to 2 sig figs. Now, this one's a little easier to do, so I'm going to round this guy up. That becomes 58,000, and this would be kilograms over milliliters. Now, we have to get these into the base units, so that's going to be the trickiest part of this question. So remember that there's 1,000 grams in 1 kilogram, so I'm actually going to multiply this by 1,000 grams to get rid of the 1 kilogram, okay, just like that. So now I get grams on the top here, and I'm going to multiply my answer by 1,000. Whoops, sorry about that. And then same here with milliliters. I know that there's 1,000 milliliters in 1 liter, so that my milliliters cancel, and I get liters here on the bottom, so I'm going to have a grams per liter. Those are the base units that I want, right? So I'm actually going to end up getting 58 billion grams per liter, which is insane and probably impossible. It's probably just you know, some random problem we had to do for this. And this would be grams per liter. Or if you wanted to put this into scientific notation, you could say 5.8, and this would be times 10 to the 10 grams per liter. Okay, either one of those would work. All right, number 4, converting Fahrenheit to Celsius and Kelvin. Honestly, this is pretty straightforward. I hope it doesn't intimidate you too much. All you really need is this equation here. And it's just a plug and chug. As long as you remember your rules from algebra, remember to do the parentheses first and then multiply. Okay, so we got Celsius. Let's do the first one here, 70 degrees, so 5 over 9. This would be 70 minus 32, which is 38. So it would be 5 times 38 over 9. This ends up being 21.1 degrees Celsius. Now the conversion of Celsius to Kelvin is a lot easier than Fahrenheit to Kelvin. Really, to get from Fahrenheit to Kelvin, we always go through Celsius. So all we do actually is we just add the number 273 Kelvin. That's just kind of the base value, and that would give us our actual value in Kelvin for the degrees in Kelvin. So that would be about 294.3 Kelvin. And I wouldn't worry about sig figs here because this is kind of just generic. These don't have decimal places, and they normally do say if they specifically want sig figs. Sometimes you do it just in case, but in this case we'll not worry about it. Okay, so for this answer we'd get 21 degrees Celsius and 294 Kelvin, and then you just do this for the other 2 values. Just plug in 100. So I get a 100 here. 109. So this would be 68 times 5 over 9. That would be 37.7 degrees Celsius, and then add 273.15, and then you end up getting 311 Kelvin about. Okay. Lastly, we'll just do the one for 250 here, so 250. Okay, and that one ends up being what? 218 times 5. Divided by 9, and then we end up getting 121.11 degrees Celsius, and then just add 273. All right, so pretty straightforward. Hopefully that's not too complicated. All right, on to number 5. Okay, so this is where we start to use a lot of math skills, and you'll want to know the concept known as dimensional analysis. This is kind of where we're going to start to introduce this stuff. So dimensional analysis is a process that we use to get from one value to another value, and in this case they're asking for how many copper atoms. Okay, so they give us some sort of some measurable length. They say here's some length of something. Find us what this means in some other term, right? And in this case they're talking about copper atoms. And so all we're really doing is we're taking this same value and we're converting it to other values until we get the value that we need. I'll show you what we mean. So we're looking for how many copper atoms. So I'm going to put this as my last unit. Your dimensional analysis will kind of look like a bunch of lines and a bunch of X's, where you have multiplication on the top. Well, it's mostly just a big fraction, kind of. And we're just multiplying all these fractions together to get what we want. So I like to make a list of the conversion factors that I have. So here's a conversion factor. 10 angstroms is equal to 1 nanometer. Cool. 2.6 angstroms is equal to 1 copper atom. Okay. So that's interesting, right? I noticed that the unit here, 1 copper atom, is equal to 2.6 angstroms. So anything that's on the top here will always be equal to whatever is on the bottom in a different unit, right? So here's 1 copper atom. It's equal to 2.6 angstroms, which is obviously a different unit. And you can kind of work backwards. So I know that they're, okay, you want to put the opposite, or the same unit on the opposite side. So I'm going to put 10 angstroms on the top here so that these angstroms cancel. And you'll see why here in a second why we do that. So then I'm going to put 1 nanometer there. And then let's see. Now I want to go from, now if I were to stop here, I'm going to put 19.05 here millimeters. The reason that we're doing this is because we're actually trying to find out how many copper atoms are in this value. And this value is the measured value and will determine your number of sig figs. Okay, so sig figs. And in this case, we got 4 sig figs, right? All right, so what I need to do is figure out how to get this nanometers into this same value. And really, they have the same base unit, so let's just use it. So we know that there's 1,000 millimeters in 1 meter, and that there's 1 times 10 to the 9th nanometers in 1 meter. And that way, these meters cancel, this millimeters cancel, and these nanometers cancel. Now, bear with me. There are multiple ways to go about these kinds of dimensional analyses. But notice that I start with my measured value. See, they said the diameter of a U.S. penny, right? So diameter of US penny, great. That's what this is. And this, I think this should really say width, actually. I think that's what they're talking about. So 19.05 millimeters. Okay, cool. Then I'm going to converting it 2 meters so that I can get it into nanometers, because I need to compare it against this conversion factor of angstroms to nanometers so that I can ultimately use that angstroms to convert it into a copper atom. Okay, and then after you figure all this dimensional analysis out, it's really easy because all you have to do is multiply everything on the top and divide it by everything on the bottom. And then that gets you your answer. So if we did that, we'd take 19.05 times 10 times 1 times 10 to the 9th. Okay, and then the other ones are just ones, right? So, and then divided by 1,000 times 2.6. And then we get this value, 7326923 1. And that's a pretty large value, but remember, we have to be specific to the 4 sig figs. Okay, so we're going to put this as, we're going to round this guy up. So this becomes 73270000. And then we'll just put it into scientific notation to kind of simplify it. So we got 1, 2, 3, 4, 5, 6, 7 places. So that becomes 7.327 times 10 to the 7th. And this would be what? Copper atoms. Okay, hope that made sense. If it didn't, kind of see how I drew it out, and even if it helps you go this way first, do that as well. That's totally fine. In fact, a lot of people do that anyway. Okay. All right, and then number 6 here. Which of the following is the smallest volume? Notice that these are all in the same base unit. They're just in different sub-units, and so it would be easiest if we can just convert them all back to the base unit. So this is already in the base unit, so I'm just going to leave it as 2 times 10 to the negative 2 liters. Okay. Now, the easiest way to do this is just to take what you have and multiply it by the change that this subunit gives you. So 2.0 times 10 to the 2. A milliliter is times 10 to the negative 3 liters, right? So I'm just going to multiply this by times 10 to the negative 3. And when you multiply these exponents together, you actually add the exponential numbers. So then you get 2 times 10, or 2.0, sorry, times 10 to the negative 1. And that is larger. Notice that the negative 1, 2 times 10 to the negative 1 is actually a bigger number than 2 times 10 to the negative 2. So this is actually smaller so far. So A so far is a smaller value. Okay, we'll do the same thing here. Here's micro. This is a symbol we call mu. So mu L, that's just microliter, is times 10 to the negative 6th. So I'm just going to multiply that by here. So 2.0 times 10 to the 7th times 10 to the negative 6th. Add these exponents together. I get 2.0 times 10 to the negative 1, or to the positive 1, sorry. Positive 1. Now that's bigger. That's still bigger, right? We're looking for the smallest volume. So this is still bigger than that. So we're going to keep going. So it's definitely not C or B. It could be A. We'll see. Now we got nano here. Nano is a billionth of a liter, right? This was a millionth. This was a thousandth. Here's a millionth times 10 to the negative 9th of a liter. And we've got 2.0 times 10 to the 8th times 10 to the negative 9th. Add these exponents together, we get 2.0 times 10 to the negative 1. that is the same as B, and B was bigger than A, so we're gonna assume that D is not the answer. Lastly, we've got these pico liters. Pico liters are 1/12 of a substance, not 1/12. Sorry. I actually don't know what that value would be. Anyway, 1 times 10 to the 12th picoliters would be a liter. Okay, so we're going to multiply these together. 2.0 times 10 to the 13th times 10 to the negative 12th. That equals 2.0 times 10 to the 1st. That's actually the same as C. So actually A is going to be the answer here. And just be wary. Remember, I've changed up these values. So it's not necessarily that A is going to be the answer on your problem set. It's just that it just so happens to be so here. All right, I hope that was helpful for part 1. Go ahead and check out part 2 for numbers 7 through 10.